Welcome to Intro to AMC 10. My name is Michael Liu, and I'm from Agora Math Circle. I created this series of videos to provide an overview of many concepts that are tested on in the AMC 10. This series of videos is provided over the course of 6 separate videos, each about an hour long. The first video, which is this video, will cover AMC 10 Basics and Geometry 1. The second video will cover Geometry 2, Circles and Polygons. The third video will cover combinatorics and probability. The fourth video will cover exponents and logarithms. The fifth video will cover complex numbers. The sixth video will cover series, equations, and numbers. So let's get started with this video, AMC 10 Basics and Geometry 1. Triangles and Trigonometry. In this video, we will first be going over the basics of the AMC 10 competition, then triangle area formulas, and then the Pythagorean theorem. Next, we'll be going over congruent and similar triangles. After that, we'll have a sample AMC 10 problem covering everything we've done so far. After we finish going over that problem, we'll cover basic trigonometry, laws of sines and cosines, and some trigonometric identities. Now please note that figures in this presentation are not drawn to scale. First, I'll be covering AMC 10 Basics. There are 25 multiple choice questions, each with 5 choices, and you must complete them within a 75-minute time limit. There are 2 separate competitions taken at different times. They both have similar levels of difficulty. Students may take both or either. It's your choice. Correct answers receive 6 points each. Unanswered questions receive 1.5 points each. Incorrect answers receive no points. This is to penalize guessing. The maximum points is 150. The allowed materials are pencils and pens, blank scratch paper, blank graph paper, rulers, protractors, and erasers. Calculators are not allowed. Around the top 2.5% of scores gets continued to the AIME. The exact cutoff varies each year. In 2020, the cutoff was 103.5 for the AMC 10A and 102 for the AMC 10B. There's a very helpful website to view previous AMC exams as well as their solutions. It is theartofproblemsolving.com. Okay, so let's get started on our math topics. The first thing I'll be going over is finding the area of a triangle. The basic formula is area equals 1/2 base times height. There is also a trigonometry formula, which is area equals 1/2 BC sine A. And lastly, there's Heron's formula, which is S is the semiperimeter, which is equal to 1/2 times A plus B plus C. And the area of the triangle is the square root of S times S minus A times S minus B times S minus C. So first, I'll be going over the basic formula for the area of a triangle, in case any of you guys need a quick refresher. So here, we are given this triangle. As you can see, the base is 11 and the height is 6. So knowing this, we can easily plug it into our formula. And we get 33 for our final area. Next, I'll be going over an obtuse triangle. In this case, we can still see that the base is 7. However, where's the height? That's not as obvious. Well, the height is always drawn down from the point opposite the base, perpendicular to it. So if we extend the base out, we can once again draw down this line. And as you can see, we have our heights. So let's say that our height is given to us, which is 6. We can once again plug it into our formula. Next, I'll be going over the trigonometry formula. Here we can see side C is 10 and side C is 7 and side A is 10. In case you're wondering, the side A is opposite angle A, so here it would be this side, and side C is opposite angle C, which would be this side. And we're given that angle B is 60 degrees. Well, we can plug this into our formula. So we have B equals 60 degrees, C equals 7, A equals 10. And we get this. It simplifies. Sine 60 degrees is the same as radical 3 over 2, which we'll be going over this later in case you don't understand what sine 60 means. And finally we get the answer to be 35 radical 3 all over 2. Now in case you're wondering why this formula works, you can notice that h is the same thing as sine 60 times 7. So this is essentially the same as the basic formula. If you don't understand what this means, don't worry about it too much, as it's not necessary to understand why these formulas work. But you could also search online if you still wish to have a greater understanding of the material. Next, I'll be going over Heron's formula for the area of a triangle. So here, S is the semi-perimeter, which means you find the perimeter and you divide it in half. So to find the perimeter, you add up the sides, right? So A equals 7, B equals 6, and C equals 10. So now we find the semi-perimeter, which is 1/2 A plus B plus C, which is 11.5. Now we plug the semi-perimeter and all of the sides into this formula. So we get this, which is equal to radical 426.9375, which is about 20.6625. The AMC 10 does not allow calculators, and it is very unlikely that you'll ever need to evaluate a radical out. So you don't need to worry about that. Here's a very condensed proof for Heron's formula. It's not necessary that you know this, as this will definitely not appear on AMC 10. But if you wish to have a greater understanding, you can search up a proof for Heron's formula. In case you're wondering what the law of cosines is, we will be going over that later. Next, we will be going over the Pythagorean theorem, a squared plus b squared equals c squared. Most of you probably know this, but I'll just go over it again in case any of you don't. So as we can see here, we're given here that a is 3 and b is 4. So we can plug this into the formula. We get 3 squared plus 4 squared equals c squared. So then we get c squared equals 25, which means that c is equal to 5. And this works in any order. If you were given c equals 5 and b equals 4, you could still plug it into the formula and you'd get a equals 3. Now, there are many Pythagorean triples. A Pythagorean triple consists of 3 numbers, which must be integers, where a squared plus b squared equals c squared. Any triangle with these 3 side measurements given is a right triangle. So this is always the case. So if you can see here, if you have this is a list of primitive Pythagorean triples. If a triangle had 3 of these side lengths, it means that it's a right triangle. So it's something important to note, as it will often come in useful. In case you're wondering what primitive triples means, it means that A, B, and C are coprime, which means that they don't share any factors. So for example, if you look at 5, 12, 13, the only number that you could divide all of them by and still get a whole number is 1. There's no other number that you can divide them all by. Triples can also be found by multiplying all 3 numbers of a triple by some factor. For example, 3, 4, 5 is a triple, as well as 6, 8, 10, which is just multiplied by 2. You can try to verify it yourself, and you'll easily be able to find that 6, 8, 10 is also a Pythagorean triple. All Pythagorean triples can be multiplied by some value to get a new triple. Now, I'll be going over congruent triangles. This is very important for many geometry problems, even for ones that don't directly involve triangles. Two figures are congruent if they have the same shape and size. Corresponding parts of congruent figures are congruent. I'll be going over that more later. There are many ways to prove triangles congruent, but I will be talking about side, 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 angle, side, angle, side, angle, 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 side, and hypotenuse, leg. If you don't understand what any of those means, it's fine, because I'll be going over those in a minute. A quick notice, there is no SSA congruence, and I'll be going over why in a moment. So CPCFC, congruent parts of congruent figures are corresponding parts of congruent figures are congruent. This includes both angles and sides. So let's say triangle ABC is congruent to triangle DEF. Now if you notice here, when two parts are corresponding, they have the same place in the triangle. So A corresponds to D, meaning that they're congruent. B corresponds to E, C corresponds to F. Also, it applies to sides, not just angles. AB corresponds to DE, BC corresponds to EF, and AC corresponds to DF. So when a figure is congruent, it means that they are exactly the same. So to start off, I'll be going over SSS congruence. What it is that if all three sides of a triangle have the same measure as all three sides of another triangle, the two triangles are congruent. Now if you look at the figure below, you can see that it's given that two sides are congruent. And in case you're wondering what those hash marks means, it means that the two sides are similar. So it means that AB is the same as AD and DC is equal to BC. Now, we need a third side to prove SSS congruence. However, we can easily see that AC is the same as AC. So we have a third side between these two triangles. So now we can prove that these two triangles are congruent. As I said before, it's given that AB is equal to AD, DC is equal to BC, and AC obviously equals AC. So triangle ABC is congruent to triangle ADC. Notice that it's very important in the order in which you name your triangles. If instead of saying ABC is congruent to ADC, you said triangle ABC is congruent to ACD, well, what you're saying then is that angle C is what you're saying then is that AC corresponds to AB, and those two are congruent. However, it's obviously not the case. Now, I'll be going over SAS congruence. So this states, if two sides of a triangle and their included side angle have the same measure as two sides of another triangle and their included angle, the two triangles are congruent. So now we can see here that's given that AB is equal to AD, and that angle DAC is equal to angle CAB. In case you're wondering, that's what these arcs mean. It means that the two angles are congruent. And once again, we can easily find that AC is equal to AC. So we write it down, AB equals AD, AC equals AC, and angle BAC is congruent to angle DAC. So that is sufficient to prove SAS congruence. So we can now state that triangle ABC is congruent to triangle ADC. Now I will be going over ASA congruence. What it is that if two angles of a triangle and their included side have the same measure as two angles of another triangle and their included side, the two triangles are congruent. So as you can see here now with our example, it is given that angle CAB is congruent to angle CAD, and angle ACD is congruent to angle ACB. And once again, we obviously know that AC is equal to AC. So we write down AC is equal to AC, BAC is congruent to DAC, BCA is congruent to DCA. And because this satisfies ASA, triangle ABC is congruent to ADC. Now, in case you're wondering what an included side or angle means, in this case, the included side is the side between the two angles. So if we're looking at angle BAC and BCA, so these are the two angles, the side between them is AC. And if you're talking about an included angle, it's the angle between the sides. So if you're looking at sides CA and AB, the included angle would be angle CAB. Now I'll be going over why SSA does not work. So you can see that we're given a triangle here, where AD equals AB. So from here we can obviously see that AC equals AC. And then also obviously ACD equals ACB, because they're the same angle, it's this angle right here. So knowing this fulfills SSA between triangles ACD and ACB, because they have a side and a side congruence and an angle right here. However, triangle ACD obviously does not equal triangle ACB. Additionally, the two triangles are also not similar, which will come in importance in a few minutes. Now, I will be going over hypotenuse-leg congruence. If a leg and hypotenuse of a right triangle have the same measure as a leg and hypotenuse of another right triangle, then the two triangles are congruent. It is very important to note that the two triangles must be right triangles. Otherwise, this congruence does not apply. So you can see here that we're given two triangles. Well, it's given that AB equals AD, and AC, once again, obviously equals AC. And it's also given that triangles ABC and triangles ADC are right triangles. So triangle ABC is congruent to triangle ADC. In case you're wondering why this works, because of the Pythagorean theorem, if two triangles have the same length for the hypotenuse and leg, or just two legs, the third side must be equal, satisfying SSS congruency. Once again, it's not too important to understand this, but since it's simpler, it's nice if you understand. Now, I will be going over similar triangles. Now, in case you're wondering what similarity means, two triangles are similar if they have the same shape. Now, what that means is that similar figures have corresponding angles that are congruent, but their corresponding sides are not necessarily the same measure. However, their corresponding sides do have measures that are in proportion with each other. What that means is that if you divide all the sides of one figure by the corresponding sides of a similar figure, you will get the same number for each division you do. There are many ways to prove two triangles similar, but I will be talking about these: angle angle, side angle side, and side side side. Now notice, angle side angle and angle angle side similarity is included in angle angle similarity, because both of them have two angles. There's no SSA similarity, which you can refer to the earlier slide. So you can see here Angle-angle similarity means that if any two angles of a triangle have the same measure as any two angles of another triangle, the triangles are similar. SAS similarity means if two sides of a triangle are proportional to two sides of another triangle, and the included angles of both pairs of sides are equal, the two triangles are similar. SSS similarity means that if all three sides of a triangle are proportional to all three sides of another triangle, the two triangles are similar. Now for an example of what it means for sides to be proportional, we're given these two triangles here. Well, it's given that angle A is congruent to angle D. We can also see that side AB is 3, side AC is 3, DE is 5, and DF is 5. Well, to test proportionality, we divide AC by DF. We see that's 3/5. We divide AB by DE. We see that's also 3/5. So what it means, since we got the same number, is that they're proportional to each other. So that's side, angle, side, because side is proportional, angle is congruent, and side is proportional. So triangle ABC is similar to triangle DEF. Now, if instead of DF being 5, it was 6, it would no longer be proportional, because AC divided by DF would be 3/6, which is not the same as AB over DE. If you still don't understand, you should probably search online for more guides, because it's very important to understand how similarity works. Now we have our first example, AMC 10 example problem. So this is problem 12 from the 2020 AMC 10A. Triangle AMC is isosceles with AM equal to AC. Medians MV and CU are perpendicular to each other, and MV equals CU, which equals 12. What is the area of triangle AMC? So first, we have a few definitions to get out of the way. An isosceles triangle means that two of the sides are equal to each other. There are also two other types of triangles: scalene, which means none of the sides are equal to each other, and equilateral, which means all three of the sides are equal to each other. So you can see here that tells us two of the sides are equal to each other and tells us which two sides, AM and AC. It's also easy to see by yourself which two sides are equal to each other. But in the AMC 10, not all figures are drawn to scale, so you should be careful about the pictures they give you. A median is a line drawn from an angle to the midpoints of the opposite side. So in this case, median MV is drawn from angle M to the midpoints of AC. So what that means is that AV is equal to VC, because a midpoint is at the middle of the line segment. And CU is drawn from angle C to the midpoints of segment AM. So if you want to give this problem a try, you can pause the video right now and see if you can solve it. It's a difficult problem to solve, but you should have enough knowledge to be able to solve it. There are many tricks that you pick up over time to help make these problems easier to solve. For this one very important thing that you could do is to draw a line for your own reference somewhere. If you want to try to figure out what that line is yourself, then you can go ahead and try to do that. Otherwise, I'll show you right now which line you can draw that would help you a lot. So a line that you can draw to help you a lot would be here, across UV. Now it's your job to figure out what to do with this line. If you still can't solve this problem, it's fine. It takes a lot of practice to learn how to solve these problems, and they're all very difficult. So now we will go over the solution for this problem. Once again, as a quick reminder, a median of a triangle is a line segment drawn from an angle to the midpoint of the opposite side. So we can see, based on this definition, that AU, which would be this side right here, is equal to 1/2 of AM, which is this entire segment. And in case you're not following, it's because AU is equal to UM. This is the definition of a midpoint. So from there you can see that AM is equal to 2AU. So AU is 1/2 of AM. And also we can see the same thing on the other side. So AV would be equal to 1/2 of AC. Additionally, angle A is equal to angle A, which is obviously true. So now we can see here that we have two sides that are proportional. AU is proportional to AM. AU is 1/2 of AM, as is AV compared to AC. And angle A is congruent to angle A. So that's enough to establish SAS similarity. So from there we can see that triangle AMC is similar to triangle AUV with a scale factor of 2. Well, the scale factor from AUV to AMC is 2. Because if you divide AM by AU, you would get 2. Well, here I said the scale factor is 1/2, which it would be from AMC to AUV. You just swap it around to the reciprocal. So the area of AUV is 1/4 that of AMC. In case you didn't know, the area of a figure compared to a similar figure is always the scale factor squared. So knowing this, the area of quadrilateral UVCM is 3/4 that of triangle AMC. The reason for this is because quadrilateral UVCM is just AMC, but you take away this triangle here, AUV. Now we know that AUV is 1/4 of AMC, so this quadrilateral that's left over here is 3/4. To calculate the area of UVCM, there's a formula to find the area of a quadrilateral when its diagonals are perpendicular. That would be diagonal 1 times diagonal 2 times 1/2 is equal to the area. So in this case, we can plug the values in and we get the area of UVCM is equal to 12 times 12 times 1/2. And that would be equal to 72. In case you're wondering why this works, it's because it's given that UC and VM are perpendicular, and that means that each of UP, VP, MP, and PC act as a height or base of the right triangles. So you can split this into 4 right triangles, or you can split into 2. So let's say split into MUV and MVC. You can see that MV is the base of both right triangles, while UP is the height of MUV, and PC is the height of MCV. Well, UP plus PC is UC, so then that means that the height times the base of both triangles times 1/2 would be the combined area. If you still don't understand it, don't worry about it too much, as I will be going over it in more detail in the next video. So thus, 3/4 of the area of triangle AMC is equal to 72, and the area of triangle AMC is equal to 4/3 times 72, which is equal to 96. Another way you could have found the area of UVCN if you did not know the quadrilateral formula is that you could have found that UPV was similar to MPC. Well, we know this because UV is 1/2 of MC, since we showed that triangle AUV and AMC were similar earlier. So because UV is 1/2 of MC, and they're also parallel because this is an isosceles triangle, we can also see that because it's parallel, there's theorem that states that alternate interior angles are congruent. So we know in this case that angle PMC is congruent to angle PVU because of alternate interior angles. And then we know that UV is parallel to MC. And also PCM, which is this angle right here, would be congruent to VUP. So that's enough to establish similarity between triangle UPV and MPC. Well, actually, I did miswrite it. Should have been triangle UPV similar to triangle CPM. So I did end up miswriting this here, so this should be the correct way to write it. And then here, so, and we know that UV is 1/2 of MC, as I stated that earlier. So the scale factor between these two triangles is 1/2. So now we can show that UP is 1/2 of PC, and VP is 1/2 of MP. So once we know that, since it's given that MV equals CU equals 12, it's easy to figure out that UP equals PV equals 4, and MP equals PC equals 8. Because UP is half of MP, so you can see that this is correct. Then the area of the 4 triangles that make up quadrilateral UVCM could easily be found. So we know that this is a right angle. We found out that this is 4, and this is 8. You can see that this is obviously 16, 16, 8, 32. So adding that all up, we get 72. And it's the exact same thing as we got here using the quadrilateral formula. If you still do not understand my solutions, you can look at more solutions at theartofproblemsolving.com using this link. I hope you understood, but even if you did understand, it's still nice to look here to see some other solutions and learn more ways to help solve this problem. Now we will be covering basic trigonometry. We'll be going over sine, cosine, and tangent. An easy way in the beginning to remember these is SOHCAHTOA, which you can see right here. What it means is for sine, you have opposite over hypotenuse. For cosine, you have adjacent over hypotenuse. For tangent, you have opposite over adjacent. And I'll be explaining what these means in more detail in a moment. And note that these are only for right triangles. So sine is opposite over hypotenuse. So as you can see here, let's say you're looking at angle B. Well, the opposite side of angle B is 4, and the hypotenuse is 5. So the sine of angle B is 4/5. Now we have cosine, which is adjacent over hypotenuse. Well, once again, if you're looking at angle B, the side adjacent to angle B, which is also not the hypotenuse, which is something important they have to consider, is 3. And hypotenuse is 5. So adjacent is 3, hypotenuse is 5, cosine B is equal to 3/5. Finally, we have tangent, which is opposite over adjacent. Once again, if you look at angle B, the opposite of angle B is 4. The adjacent side to angle B, which is also not the hypotenuse, is 3. And we don't count the hypotenuse because it just messes things up. So the tangent of B is 4/3. quite a few important angles in trigonometry that you should memorize the values of, because these appear very commonly in many problems. The given angles are in degrees. Sine 0 equals 0, sine 30 degrees equals 1/2, sine 45 degrees equals radical 2 over 2, sine 60 degrees equals radical 3 over 2, sine 90 equals 1. Cosine 0 equals 1, cosine 30 equals radical 3 over 2, cosine 45 equals radical 2 over 2, cosine 60 equals 1/2, cosine 90 equals 0, tangent 0 equals 0, tangent 30 equals radical 3 over 3, tangent 45 equals 1, tangent 60 equals radical 3, and tangent 90 is undefined. There are a few formulas involving these trigonometric identities that come in very helpful in many problems. First, I'll be going over the law of sines. What this is in all triangles, sine of angle A divided by A equals sine of angle B over B, which equals the sine of C, angle C over side C. So once again, remember that lowercase letters usually represent sides, while uppercase letters usually represent angles. And the same letters are opposite to each other. So here we're given this triangle. We see that C is equal to 7, B is equal to 6, and angle B equals 30 degrees. So we are told to find angle C. Well, here we can use part of the formula. Since we're given angle B and side B, we use this part as well, and since we need to find angle C, we use this part. And we can just ignore this part. So we have sine B over B equals sine C over C. So we plug it in. The sine of 30 degrees over 6 equals the sine of C over 7. So we can just use basic algebra, multiply both sides by 7, and we get 7 sine 30 degrees over 6 equals sine C. So remember last slide where we went over trigonometric values of common angles? Sine 30 degrees is equal to 1/2. So then we get, that should be sine C. Then we get sine C equals 7/12. And angle C is roughly equal to 35.7 degrees. Now, this 35.7 degrees was found using a calculator, and it's very, very unlikely that you'll need to find the exact value of an inverse trigonometric function. So usually just being able to get to this step, sine C equals 7/12 is enough. However, sometimes you will need to know the value of common angles in trigonometric functions. So say you got sine C equals radical 3 over 2. You would need to know that C would be equal to 60 degrees. So next, we'll be going over the law of cosines. What it is that in all triangles, a squared equals b squared plus c squared minus 2bc cosine angle A. Now notice that this can go in any order, but the cosine of the angle must always be the angle corresponding to the side that you put first. So you can see here b squared equals a squared plus c squared minus 2ac cosine b, and c squared equals b squared plus a squared minus 2ba cosine c. So whatever side you put first, that's the angle you put in cosine. And then the other two sides, you go here, a squared plus c squared minus 2ac, or whatever sides you have. Now you notice that this looks kind of similar to the Pythagorean theorem. And, well, what if you use it as the Pythagorean theorem? Say c is the hypotenuse, and you're looking at this. Well, you would have c squared equals b squared plus a squared minus 2b A cosine. Well, since C is the hypotenuse, the angle opposite the hypotenuse is always 90 degrees. However, you must also remember that the cosine of 90 degrees is equal to 0. Well, anything times 0 is just 0. So this entire thing would be 0. So as you can see here, you have the Pythagorean theorem. C squared equals B squared plus A squared. So anyways, that's not that important to remember that, but it's just something interesting to notice. So here we have a triangle, and we're given that side C is 10, and side B is 6, as well as angle A, which is 120 degrees. Well, we need to find side A. Well, this perfectly falls into the formula of the law of cosines. We're given side B, side C, side B and side C, as well as angle A. So we have everything we need to plug it in to find side A. So we plug everything in. A squared equals B squared, which is 6 squared, plus C squared, which is 10 squared, minus 2 times B times C, 6 times 10, times cosine 120 degrees. Well, we see now that A squared equals 36 plus 100 minus 120 times negative 1/2. And you might be wondering, well, how do we know that cosine 120 degrees is negative 1/2? Well, I'll be going over that in a few minutes, once we get to trigonometric identities. So now we see that A squared is equal to 196 because this adds up to 136, and this becomes 60. And then we have A equals 14. So this is how to use the law of cosines to solve for sides of and angles of triangles. Finally, we will be talking about trigonometric identities. Some of these are very important and are very helpful in solving problems related to trigonometric identities, related to trigonometry. There are many trigonometric identities that can be used, and I encourage you to find more that I have not listed here. So the most important ones are sine 90 degrees minus alpha equals cosine alpha, where alpha is just any angle, and cosine 90 degrees minus alpha is equal to sine alpha. It's also tangent alpha is equal to sine alpha over cosine alpha. So in case you're wondering why tangent 90 is equal to 0, this is why, because tangent 90 would be equal to sine 90 over cosine 90, but cosine 90 is 0, and you can't divide by 0, so that would be undefined. Another very important one is sine squared alpha plus cosine squared alpha equals 1. There's also sine of negative alpha is equal to negative sine alpha. Cosine of negative alpha is equal to cosine alpha. And tangent of negative alpha is equal to negative tangent alpha. So if you made the degree and sine negative, you get the negative value of the sine without the degree being negative. But if you switch the sign of the degree with cosine, it would still be the same if you had not switched the sign. Next, you have a few here. These aren't covered commonly on the AMC 10, but still nice to know. So there are 3 more trigonometric functions here: secant, cosecant, and cotangent. These are basically the reciprocals of the original 3 covered earlier. Secant alpha is 1 over cosine alpha. Cosecant alpha is 1 over sine alpha. Cotangent alpha is equal to 1 over tangent alpha. And then there are 2 more here. 1 plus cotangent alpha is equal to cosecant alpha, cosecant squared alpha. Tangent squared alpha plus 1 is equal to secant squared alpha. And in case you're wondering, if we have sine squared alpha, that's the exact same thing as sine alpha squared. The reason it's written this way is to avoid confusion on if you written it this way. It'd mean that you're writing it as the sine of the angle squared. So instead, you want to write it this way. So these are only some of the more commonly used identities. For a more extensive list, you can look at this link. If you want to memorize some of these, I definitely recommend that these are more important. One final note that I have to add is that finding the value of cosine 120 degrees or any angle greater than 90 degrees is actually not beyond the scope of this course. So we can actually use these trigonometric identities shown here to find the value. So we have cosine 120 degrees. Well, we can convert it to sine using this trigonometric identity. So that would be sine 90 minus 120, which is negative 30 degrees. Well, then we have sine negative alpha equals negative sine alpha. So that means that sine negative 30 is equal to sine negative sine 30 degrees, which is equal to negative 1/2. And we have found the value of cosine 120 degrees. There are proofs behind all of these identities, and if you would like a bit of practice, it would be great for you to try to find these proofs on your own. Or you could just search them up and try to further your knowledge of these identities. Either way, it's nice to know the proofs behind them, and it'll help deepen your knowledge. So this concludes the first video of the 6-part series on Intro to AMC 10. There's still much more depth to cover about triangles, and I encourage you to practice problems about the AMC and learn more about triangles on your own. They truly are very important to solve any other kind of geometry, whether it be circles, quadrilaterals, or any kind of other polygon. I hope you have enjoyed watching this video and that you've learned something new. Thank you.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end. So bye!